What's up everybody, and welcome to part 4 of my coding a decision tree classifier from scratch video series. In the previous videos we built the first 3 helper functions, and in this video we're going to build those 2 remaining functions. And actually the next one would be this one, the lowest over entropy, but we're going to build first this split data function because it will come in handy when we are going to create this function. So let's now first create a subheading for this one. So we're going to say split data, and let's also call the function simply split data. And here we pass in obviously our data, and then we also have to determine where we are going to split this data. And this is determined by 2 parameters. The first one is that we have to decide along which feature we're going to split the data. So for example, along the pattern width, or maybe also along the pattern length. And in the context of our numpy 2D array, this means we have to decide along which column we are going to make the split. So the second parameter for this function is the split column. And now let's say we want to make the split along the pattern width. The next question that we now need to answer is at exactly what point or value do we want to make the split. So for example at 0.8 or maybe 1.2 or maybe 1.6. So the third parameter for this function is the split value. And then the function should return 2 numpy 2D arrays that are the result of splitting this input data. And the first numpy 2D array should then contain all the data points that are below the split, and the other one should contain all the data points that are above the split. So the function should then simply return the data below and the data above. So now let's say we want to create this split at a pattern width of 0.8. So we're going to set the split column to 3 for now, because 3 is the index of the pattern width, the column index, and we're going to say the split value is 0.8. And now how this split function should work is that we say, okay, we have our data, and which looks like this, and here we are interested in this 4th column because that's the index of our split column. And here we're going to look if that particular value is below or above our split value. And then we're going to pick all the rows where this value is below the split value, and then we're going to put those rows into the data below variable, and all the rows where this value is above the split value we're going to put in this data above variable. So obviously then for this function we need to access this particular column, and as already seen in the previous videos, we're going to do that by saying brackets and then colon to get all the rows, and then we pass in the split column to get that particular column. And now if I run this, we get an array that only contains the values of this column. So let's store this array in a variable called split column values. And now to know which of these values is below our split point, our split value, we simply say split column values smaller or equal to the split value. And this now returns an array that contains only booleans. And the reason why there are only trues at the beginning followed by only falses is the way that our data is structured, because first there are only the iris-tosa flowers stored, then come all the iris versicolor, and then come all the iris virginica flowers. And as we've seen now many times in this diagram, only the iris-tosa flowers have a pattern width below 0.8. And that's the reason why there are only 2 values at the beginning of this array. And this Boolean array now we can use to index our data. And accordingly, this is then called Boolean indexing. And we do that by putting this expression into brackets, and then we write data before it. So what this does now is that we will get only the rows of this data where there is a true value. So if I run this now, we get a numpy 2D array that only contains the Iris-setosa flowers. So, and that's obviously our data below variable. And in the same way we can determine this data above. So let's just copy that and paste it. And now let's change the below to above. And here the split column values should be larger than the split value. And this is already our split data function. So let's copy that and paste it into the definition of the function. And now let's run it and see if it actually works. And so we're going to say data below and data above equal split data, and we put in our data and the split column, so this one, and the split value. So let's run that. And now to see if it actually works, we're going to create another scatter plot. So we're again using the Seaborn function lmplot. And here, this data argument of the function only takes in a data frame. So we have to first convert our data into a data frame. So we're going to say plotting df equals pd data frame, and we put in our data, and the columns of this new data frame should have the same names as our initial data frame. So, and we can get those by saying df.columns. And now we're going to put in this plotting df, and then we say x equals petal width, y equals petal length, and then we're going to set the fit argument to false, size to 6, and aspect to 1.5. This is now our scatter plot. And now let's also plot a vertical line that represents our split. So we're going to say plt v-lines, x is our split value, y min is 1, and y max is 7. So let's run that, and now we have our split. And now let's only put in the data points, our data below. So now we should only see the data or the dots to the left of this line, and those on the right should be gone. So let's run that, and indeed we only see the dots to the left of this line, but this plot is relatively difficult to compare to the previous one because the range of the x-axis changed, and that's because we only plotted those points. So let's plot all of our data again, and now to avoid that the range of the x-axis will change, we're going to set the limits for the x-axis. So we're going to say plt xlim, and the limits should be 0 and 2.6. In this way, we now get, so to say, a fixed view on this data. So if I now only put in our data below, we should only see those dots remaining, and those should be gone. So let's run it, and indeed that's the case. So now let's plot all of our data again, and now let's just put in the data above. So those data points should remain, and those should be gone. And that's the case. So this function seems to be working properly, and now we can start building the last helper function, which is this lowest our entropy function. And what this function should do is it should look at all the potential splits from this function and then determine that one split that results in the lowest overall entropy. And therefore, obviously, we have to first calculate, or we have to be able to calculate the overall entropy. And to calculate that, we have to be able to calculate the entropy. So let's create first two helper functions that do those calculations for us. So now let's quickly create another subheading for that function. So we're going to say lowest overall entropy. And then the first function that we're going to build is the one that calculates the entropy. So we're going to say calculate, we're going to name it calculate entropy. And here we want to calculate the entropy for such a partition of the data. So the input for this function is again just some data. And then it should obviously return the entropy. And to calculate that, we have to determine those probabilities for each class. And to do that, we obviously have to access the label column again. So we're going to say label column equals data brackets column to get all the rows, and then -1 to get only the last column, which is the label column. And now to determine the actual probabilities of those classes, we have to know how often the classes appear. So we have to begin using the numpy unique function, and we pass in our label column, and we set the return counts argument to true. So this way we now get again those two arrays, and we only need the second one. So we're gonna write an underscore for the first one because we don't need it, and then the second one we call counts. And let's also for now print this counts array. And now to determine the actual probabilities of the classes, we have to divide each number of this array by the whole sum of this array. And we can get the sum simply by writing counts.sum. And the good thing about numpy is that it does element-wise operations. So to get now the probabilities of these classes, we simply can say counts divided by counts_sum. And what this does, it will divide each number by 130. And that way we can get now an array that contains the probabilities. So let's store that in a variable called probabilities. And let's also delete this line again. And now we can use those probabilities to calculate the entropy simply by using this formula. So we're going to say entropy equals probabilities times the negative of the logarithm base 2 of those probabilities. So minus, and then to calculate the logarithm base 2, we're going to use a numpy function which is called log2, and here we pass in simply our probabilities. And here again we're taking advantage of the element-wise operation of numpy. So this function will calculate the logarithm base 2 of each probability, so of each element in this array, and then finally the first element of this array will then be multiplied with the first element of this array, and so on. And then we want to have the sum of this array, right? This is the summation sign. And this is already our calculate entropy function. So let's copy that and paste it into the definition of the function. And now let's see if it actually works. So let's write calculate entropy of our data below. So here's the data below, and the split value is still 0.8. So we should get an entropy value of 0. So let's run this, and indeed we get a 0. And now let's put in the data above, and here we should get an entropy value of 1, and we do. And now let's also calculate the entropy values for this split. So let me enlarge that, and here we can see this split is at a pattern width of 1.05, and that's because those dots are at 1 and those at 1.2, and the split is exactly in the middle of that. So let's set the split value to 1.05, and then we run the split function again to create a new data below and data above. And now when we calculate the entropy of the data above, we should get a 0.996. So that's the case. And now let's also finally calculate the entropy of the data below, and here we should get a 0.516. So let's run it, and indeed we get 0.516. So this function seems to be working, and we can now create the next function that calculates the overall entropy. So let's also call this simply calculate overall entropy. And here we want to calculate the overall entropy for the whole plot. So we have to pass in both partitions of the data. So our data below and the data above. And then obviously the function should return the overall entropy. And to calculate that, we need to know those p-values or the weights. And to calculate those, we have to know how many data points there are in total in our data. So we're going to say n data points equals length of the data below plus the length of the data above. And then with that we can calculate those weights. So we say p, so the weight for the data below equals length of data below divided by n data points. In the same way we can calculate the weight for the data above. So let's just copy that and paste it, and now we write above, and here also above. And this is already everything we need to calculate the overall entropy. So we're going to say overall entropy equals the weight for the data below times the entropy of the data below. So we're going to say calculate entropy of data below, and then plus p data above times calculate entropy of the data above. This is already our calculate overall entropy function, so let's copy that and paste it into the definition of the function. And now let's see if it works. So we're going to say calculate overall entropy of the data below and data above, and the split value is still at 1.05. So this function should now return an overall entropy of 0.804. So let's run it, and indeed it returns 0.804. And now let's set the split value to 0.8 again. So this split, so let's run the split data function again, and now this function should return an overall entropy of 0.646, and it does. So this function also is working. And now we can finally create the actual lowest overall entropy function. And as always said before, the purpose of this function is to look at all the potential splits from this function and determine that one split that results in the lowest overall entropy. So it should, so to say, find out of all those potential splits, find the best split. So let's call this function determine best split. And here we put in our data, obviously, and the potential splits from this function. And what this function then should return is the parameters of the best split. And like here in the split data function, the best split is then characterized by the split column and the split value. But not just any split column and split value, but the best split column and split value. And how this function now should work is that we're going to create a variable called overall entropy, and we're going to set it to an arbitrary high value, and then the function should simply loop over all the potential splits, calculate the overall entropy that would be the result of that particular split, and then if the overall entropy of that particular split is lower than our initial overall entropy, then we're going to store the parameters of that split into our best split column and best split value variables. So let's have a look first at what this potential splits variable looked like. So we're going to say get potential splits from our data. And now let's run this. And as you can see, this was a dictionary where the keys are the column indices and the values are lists, or the value of that particular key is a list that contains all the potential splits. So let's store this dictionary in a variable called potential splits. And now to loop over all those potential splits, we're going to say for column index in potential splits. So this will loop over all the keys. And then to loop over all the elements in the lists, we're going to say for value in potential splits brackets column index. And now to calculate the overall entropy for that particular split, we need our data below and data above. So we're going to say data below, data above equal split data. And we pass in our data, and then the split column will be this column index, and the split value will be this value. And with those now we can calculate the overall entropy. So we're going to say current overall entropy equals calculate overall entropy, and we pass in our data and data below and data above. And now we're going to check if that current overall entropy is smaller than this initial overall entropy. So we're going to say if current overall entropy is smaller than the overall entropy, then we're going to update this variable. So we say overall entropy equals the current overall entropy, and then we're going to store the values or the parameters of that particular split into this best split column and best split value variables. So we're going to say best split column is this column index, and the best split value is the value, so this value here. And this is already our determine best split function. So let's copy that and paste it into the function. And now let's see if it works. So we're going to say determine best split, and we put in our data and the potential splits. And from the videos where we talked about the theory behind this algorithm, there we determined that the best split would be at a pattern width of 0.8. But actually it could also be this split at a pattern length of about 2.6. And that's because both splits essentially separate out those isotosa flowers from the rest. So this function should return the characteristics from one of those splits. So let's run it to see what it does. And it returns this split. and that's because the column index of the pattern length is 2 and the value is 2.6. And now I would like the function to actually return this split, and that's because simply so that later on when we build our decision tree algorithm, that decision tree algorithm will create the same tree that we had in our videos where we talked about the theory. And to now do that, we only have to make one small change to the function, and it's here. So instead of just updating this initial overall entropy when the current is lower than this overall entropy, we're going to say, or we're going to update it when the current overall entropy is smaller or equal to the initial overall entropy. And that way we should get this split because the column index of the pattern width is 3, so it will come up later in this for loop, but it will result in the same current overall entropy as this split. So this if statement will be true, and then the variables will be updated. So now let's run this again. So now in this case it should return a 3 and a 0.8. So let's run it, and indeed it does. So now this function also seems to be working, and we are done building all those helper functions. So we can now finally start to build the actual decision tree algorithm. And this will be the topic of the upcoming video. So thanks for watching, and hopefully I will see you in the next video.